So now I want to get beyond 3 dimensions, starting maybe with 4 dimensions, right? And a little higher, and see how can we represent stuff. So we want to get up to some place that is a little unusual, right? That we're not accustomed to, but still be able to see patterns in data and try to make some inferences. And just like every step that we've taken so far, as we're doing things that are a little more high dimensional, it takes a little bit of training, a little bit of thinking hard about what are the presentations before you, what do they mean, and how might they relate one to another. Okay? So what you're familiar with is, being math students, Cartesian coordinates, right? So this is from René Descartes, where every variate has a particular position on one of the axes, and that works pretty well with up to 3D. Beyond 3D, we kind of get in trouble in sort of drawing that. Of course, the mathematics doesn't care. Math doesn't care. There's nothing special about 3 or 2D or 1D, right? That's just what we're accustomed to. So we can do things mathematically in much higher dimensional spaces. And so what we want to figure out, can we visualize that? Since the visualization, we're stuck with just 2 or 3D. In fact, the 3D we kind of fake ourselves with motion or with perspective or stereo fusion. Okay? So here's a classic data set. If you've been in statistics any length of time, you'll have run into this data set more than once. It's one that people like to use because it's just got 4 dimensions and it's got 3 different groups of data points. And so the idea is that we've got measurements on 3 different flowers, 3 different species of this iris flower. These are taken largely, many of them are from the Gaspé Peninsula. So there's a true Canadian angle here looking at these different irises. And the measurements that were taken are 4. These long pieces of the flower are actually the sepal. Okay, the thing that encloses the petals. The shorter ones are the petals themselves. And so for every flower, we've got a measure of the length of the sepal and the width of the sepal, the length of the petal and the width of the petal. And then we also know which of these 3 species it is. So 3 different species of iris. Okay? In learning from maps, what we might do is represent every one of these points in the 4-dimensional space by a glyph. Now, a very natural looking glyph for these particular collection of measurements is just using this rectangle, because we know that the petal is fitting inside of the sepal. And this is in fact what Edgar Anderson, the botanist who collected this data, actually used, and produced these glyphs. So we see that from the sepal we've got the height and the width, and then we've got the petal, and we just cut that out. So that little image represents that one flower. It's another flower. Okay, so we're just going to use those glyphs. And then we can look at the group of flowers. So here's a bunch that are of the same species, Setosa. And you can see they seem to have a similar sort of shape. Going back to the original slide, it looks kind of like SpongeBob's shape. We've got these very tiny slits that correspond to the tiny petals. And in the center, this is the average. This is the glyph that corresponds to the average of all 4 measurements. Okay? Versicolor, different species, looks quite different. The glyph is quite different. So you know that it's in a different part of the 4-dimensional space. But they all seem to be kind of clustered. These look much more alike, and they look like each other and different from that one, and these look alike but different from a versicolor. Again, the glyph is the average. So these are the natural ones that Edgar Anderson used back in the early part of the 20th century. And what he did then is he took these averages and he compared these 3 species. Setosa species on the right, this one here, the Virginica on the left, and the middle one is versicolor. And line these up, and interesting aside here is that what his interest was how to place this center one, versicolor. And the funny thing about flowers, so the thought is that this flower looks like it has a habitat that's somewhere between the habitat of these two. It looks like maybe it's a hybrid of these two. And in fact, each one of these flowers have different numbers of chromosomes, which is curious. And the ratio of chromosomes places versicolor about a third of the way along between the number that's in Virginica and the number that's in Setosa. And so the hypothesis is that about a third along. And in my mind, absolutely stunningly, if you look at the averages and you draw these little strings connecting them, sure enough, those measurements of sepal width and sepal length seem to place that flower about a third of the way along. So somehow he's thinking like in 4D space, the positions of, you imagine there's a point cloud for this end, which would be Virginica, and a point cloud for this one, which would be versicolor, a point cloud for that one, which would be the species Setosa, that this point cloud is in some way a third of the distance between these two point clouds in 4D space. So I think that's probably a remarkable fluke that those sepal widths happen to correspond to the number of chromosomes. But there you have it. That's what he was interested in. Okay, so those are natural glyphs for those particular flowers. And the sense is that they're kind of like cartoon versions of the petals themselves, the petals and the sepals themselves. And we might think, well, what would be a natural glyph for us? And if you remember the Bush-Obama faces, well, maybe faces are pretty good for us, right, to represent data. Like I can, again, distinguish every one of you from each other. I can see some look more like each other and some look very different from each other, right? So I can tell people, I probably know you by face a lot better than I know you by name, right? So Herman Chernoff, back in 1973, thought, well, wouldn't this be a good idea to represent multivariate data points? Now, back when I was a grad student, I thought this was actually, when I first heard of Chernoff Faces, I thought, wow, this is some mathematical object. But no, these are the cartoon faces. These are not faces of some high-dimensional polytope. These are cartoon faces. And so you need a rule of mapping your multivariate data, your measurements, to a face. And Herman, and there's the original real Chernoff face, that's Herman on the left, chose a particular measurement about the shape of the cartoon face, related to the length of the nose. He had ears and he had eyes, and where the pupils were located, and the angles of the eyes, and how big the jaw was compared to the top of the head and the mouth, etc. And that means you could take numerical values, right, and map them onto these geometric features of this cartoon shape, cartoon face. And that's what Herman suggested. And so we look at some of his original data. This is looking at some geological data. And how you start to think, well, all those glyphs, I'm mapping a lot of high-dimensional data onto faces. Can I tell which guys look alike? Which guys look like each other? Which guys look different from each other? Is it really easy for me? Right, so definitely these guys all look kind of alike. That guy looks weird, right? He stands out in the crowd, so he's a bit different from his companions, although he's alike in many other ways. And similar to these guys, and then there's a couple of kind of angry guys in the middle, and maybe this, this guy looks a little bit like those guys. So you start to think about, can I at least cluster these points in high dimension just by what do they look like? Because we're really, really good at that. Remember, you've got neurons that are firing for faces. Okay? So there are some Chernoff face software available in R and in lots of other places, but in the teaching demos package, somebody's written a package that will just draw these things, and so it'll map up to 18-dimensional data into these different features of a face. So you've got the width of the center, the top versus the bottom width, the height of the face, down to distance between the eyes, the angle of the eyes and eyebrows, how elliptical are the eyes, and things about the mouth, curvature of the mouth and the nose, okay? So for example, here are 3 of the iris data. These are the, from, I guess the left is, if I remember correctly, this is going to be the first guy in Setosa, the first one in versicolor, and the first one in virginica. And sure enough, they look kind of different. But I've only mapped to 4 features. I've mapped to these features, 8, 13, 14, and 17. That is, what did I say, 8, 13, 14, 17? So 8, curvature of the mouth, 13, the circle, ellipse of the eyes, 14, the size of the eyes, 13, 14, and 17, angle of eyebrows. So the other features are the same. So you can tell that they kind of look different from each other. And with appropriate other software that other people have done, just allow us to investigate this to see what the effect of these various values are. What happens here is I've got a 3 glyphs, and this is the minimum value on all of these values. This is the maximum value. So those are the extremes of the faces. This guy that looks like the moon, and this guy that looks, I don't know what he looks like. And this value has all of these values that are on this slider. So you can see some center, but you know, the center width here, from the maximum center width to the minimum center width, top bottom width. So each one of these would be a variant that you're looking at, the height of the face overall. And you can see they look like they're kind of confounded sometimes. Okay. Eye shape. Eye angle. So eyes between. So make this guy eyeball position. So you can have all of these different kinds of looking faces, and it's just a matter of what is the value here. So eyebrow angle, eyebrow width, where's his mouth? Mouth height, and curve. Okay, so we've got at least 18 dimensions to play with. So if I take, if I choose, I have to choose, if I only have 4, I have to choose which features am I going to map my 4 variates to, which features of the face. So if I choose different features, I'm going to see different kind of displays. So now I'm looking at 6, 7, 8, and 12, so it's a slightly different. Same data points, same points in a 4-dimensional space rather. And again, I guess with only 4 dimensions, we can still see some difference between those. Certainly the eyebrows are drawing a lot of it, and the mouth and the nose length, it looks like. Okay. So if I look at, for example, all of the irises, this is in random order, on those 4 features, I should have probably, should be, yeah, 150 faces. Now you say, can I group those? Can I say which of these faces look alike? Can I identify groups? Right? Are all these guys here that look kind of spooked in the same group? These 2 in the same, these 3 in the same group? So you begin, if you had these, if you could move them around, drag and drop them, move them around, you can imagine that you'd say, okay, those guys kind of look alike, these guys kind of look alike, and you've got some way of visually clustering it. Maybe you can separate out these 3 different species of flower, of iris. Okay, any questions? So that's in random order. If I had them in non-random order, you'd be able to tell because the first 50 are of each. So here's the olive data, which has 8 dimensions. So now I've got 8 facial features mapped out from the data. And you remember these are olive oils and they're in different geographic regions. And the question is, which of these look alike, which of these look different? You know, first thing you might be attracted to are trying to get all of the small guys in the same group, and then separating them out within that group. You know, this fellow here maybe looks a bit like that fellow over there. Okay? So you can play with that. Think about, can I sort those out into different groups, and do those groups then correspond to the regions where these olive oils are from? And are some groups closer to each other than other groups? Problems, of course, is we're very good at faces, but we also focus on particular features. So this is a typical eye tracking example. If you're looking at eye movements, when somebody looks at a photograph, you can see where their concentration is over here. These are just where their focus is. A lot of focus on the eyes and around the nose and the mouth. And that's probably where we tend to look when we're looking at faces, to look for features. So one of the really significant problems with cartoon faces is that not all features are the same. And you'd like to have the mapping from data to the display to be independent of the feature, right? Okay. So, as much fun as that is, it turns out not to be such a great idea. Okay, the mapping from data to the face features is perhaps not that good. Although sometimes I've seen it being useful for an infographic, where you put all the happy faces that correspond to, you map all the positive aspects to happy parts of the face, so you can see where all the happy stuff is. So you're adding another dimensionality, associating positive things with happiness and negative things with sad faces. So for the infographic, then you're just trying to get the information quickly. But for exploratory work, not so good. Well, here's another way of trying to get at high dimensional information. Another historical one. This is Florence Nightingale. And if you don't recall the history here, Nightingale was a nurse working with the British Army during the Crimean War of that time, and looking at deaths. And so she's looking at a time changing here from April 1854 to May, June. There's an event here, Bulgaria, July, August, September. Crimea happens here, October, November, December, January, etc. So there's a full year. So there's a time series going around here. And then what she's done is she's taken, for each time series, a wedge. So the length of this wedge is proportional to some measurement. The measurements are, the red is the number of deaths attributable to wounds, red wedge, deaths from wounds, etc. The black are from all other causes. The blue ones are from diseases. And so this is where we begin to worry about, things being actually antiseptic and physicians washing their hands and keeping things clean. So before this is not known. So the idea is, however horrible that war is, and the people dying from wounds here being very large, far greater number die from just disease, from infection afterwards. And so this is meant to convince the British that they perhaps should have a little more concern about the hospital conditions, because they're losing more people to that than they are to battle. Okay? So, in this particular case, the area is proportional to the value. So that's a famous plot that's sometimes called Nightingale's Rose plot, which she made sort of one of the first female statisticians in history, and making a great deal of use of graphics, and that's her invention. But you'll see that historically, here's something from an Atlas of Britain and Northern Ireland in 1963. We're seeing something like the rose plot here, the wedges coming out, talking about various employment. I can't read it, unfortunately, so I imagine there are different sectors of employment located spatially. And again, here above factory building, where now it's just like blades of a fan coming out, but essentially the same idea. Well, you can get that in R. So they're called stars. And to get Nightingale's roses, almost, you just want to have draw segments equals true. So we've got some data, and I'm just going to take a sample of that data, or just sort of reorder the data and allow you to look at that. So there's the iris data now with Nightingale's roses using the stars plot, okay, with segments. One of the unfortunate things here, I believe that the segment length is actually proportional to the value, which maybe you want it to be proportional to the square root of the value because you're picking up area. Right. So now you say, well, which one of these are like the others? So there's all these little guys with the red on the top left that you might group together. And there's then these other ones with black here, and they seem to have different sizes. So you'd certainly separate off these little ones with the red in the top left corner being the dominant thing. And I believe that probably is Setosa. Advantage here, all of the variates are treated the same, right? All of the variates are the same. It's not like the faces, right? Where mapping to the eyes may be more important than mapping to the orientation of the eyebrows. Okay. Here's the olive data. We've got 8-dimensional data now, so we've got a lot more going on there. It's again a subset of the olive data. And think about grouping those. So pretty much what you can do here is some kind of, again, visual clustering is what you're stuck with, looking at which of these look most alike. So I might say, you know, maybe those two certainly look more alike than they look like this thing. That looks more like that, which looks like this, etc. So you can start grouping based on the shape and the distribution of the colors. Okay. So some remarks. So the use here is different from Nightingale's. Nightingale had a time series and used overlapping segments so that you had, going back here, you see that she had, it looks like a rose, and that, you know, got these petals, these layers of different petals. And we're more interested in having each wedge represent one variate value, with no overlapping at all.